It's now my pleasure to introduce the first speaker of our technical program, Dr. Albert Hofstra. Albert is an economic geologist and geochemist at the United States Geological Survey in Denver, where he has conducted research on the origin of hydrothermal ore deposits for 37 years. Since 2011, Albert's research has focused on ore deposits containing critical minerals.
Hi, my name is Al Hofstra, and I lead the USGS Systems Approach to Critical Minerals Inventory Research and Assessment Project in Denver. I got involved in the Critical Minerals Mapping Initiative because it has similar goals, but on an international scale. My goal today is to describe the deposit classification scheme that the CMMI working group developed for the Global Geochemical Database on ore samples. Vladimir Lysitsyn and I prepared this report with input from everyone in the working group. We thank our associates for valuable input and discussions that made this a better product. The open file report has 5 pages of text and 2 tables with 36 pages devoted to the classification scheme and 17 pages of references. The background section describes the steps taken by the US, Australia, and Canada to identify and ensure the supply of critical minerals before and after this project was established, as described in the preceding presentations. The problem section states that this report pertains to the initial goal of the CMMI to compile multi-element geochemical data on ore samples from myriad deposit types around the world and provide the data to the public. It goes on to say that a classification scheme with standard nomenclature was needed to effectively sort and use the multi-element geochemical data. The approach section describes the hierarchical relationships that exist between system types, deposit environments, deposit groups, and deposit types, and how we standardize deposit type nomenclature. The resulting classification scheme is then presented in Table 2 and its potential uses discussed. Critical minerals are commodities such as elements, compounds, or minerals that are vital to the economic and national security of individual countries. Many are vulnerable to supply disruption. Table 1 shows that between our 3 countries, there are 39 critical minerals. More if platinum group and rare earth elements are split out. So to be useful, the geochemical data generated on ore samples had to include a large number of elements. The data sets contributed by each country fulfill that requirement and often include values for 60 or more elements. To put the classification scheme in context, it's important to explain why and how it was generated. First off, even though we all speak English, the working group had trouble communicating and agreeing on things because the same words have different connotations or different words have the same meaning in each country. To facilitate communication, we needed uniform terminology and definitions. Second, to facilitate apples-to-apples comparisons of the geochemical data on ore samples, we needed to relate the samples analyzed to a single set of deposit types. Third, to place the geochemical data into a systems framework, we needed to relate the deposit types to ore-forming environments and system types. To do this, the working group met twice a month for over a year. We debated the difference between a system and an environment and eventually came to a consensus. We considered the deposit types names used in each country and narrowed it down by settling on a single name with synonyms, examples, and references. For deposit types, we took into account common usage, tried to avoid names with various issues, aimed for a consistent hierarchical level, and used a consistent format. The report captures what was agreed upon, but does not provide a justification for each of the 189 deposit type names selected. While the scheme is fit for purpose, we recognize that it is far from perfect. We hope that it will spur discussions in the economic geology community to standardize terminology in the future. This effort required us to agree on names for 189 deposit types, 12 deposit environments, and 40 system types, as well as the meaning of the terms used. We also had to agree on the membership of deposit types in each environment and system type. We found it easy to agree on deposit environments because the terms and definitions are in common use. For system types, we had to define the scope of each system and in many cases generate new names, which was difficult and wasn't completed by the April deadline for this report. At that time, we were able to agree more or less on what each system type entailed, but not the names. So we added a column called Genetically Related Features that is a proxy for system type. At our last meeting, we finally agreed on 40 system type names, which will be incorporated into a future update of this report, as well as the Global Geochemical Database. So until that is done, only 3 categories, deposit environment, deposit group, and deposit type, have been linked to the sample entries in the Global Geochemical Database. The following example illustrates what we mean by system type and genetically related features. The well-known porphyry copper system of Sillitoe is equivalent to our calc-alkaline Porphyry-Epithermal system. We selected this name because it has a petrology term and it specifies that the system includes epithermal deposits. The genetically related features entry for this system type is ARC, magnetite series, calc-alkaline volcano-plutonic center, magmatic fluid, alkali and hydrolytic metasomatism, and myriad deposit types. Analogous entries are provided for every system type in Table 2. In this case, the genetically related features entry is meant to conjure up a picture of a subduction-related magmatic arc with magma columns that extend from the base of the crust to volcanoes at the surface, or deposits form at the top of the system. In productive magmatic centers, fluid exhaled from cooling plutons is discharged into porphyry stocks and outward into country rocks saturated with heated groundwater. An array of cogenetic deposit types containing a variety of commodities form as magmatic fluids cool and react with country rocks and groundwater in the trap part of the system. The classification scheme captures the one system to many deposit types relationship shown here and designates the environment as magmatic hydrothermal. This approach has been applied to the deposit types that occur in the trap part of each system type. The critical minerals thought to be associated with the deposit types in this system are shown in blue. The Global Geochemical Database will enable us to trace critical minerals through systems and quantify their abundance in each deposit type that has been sampled. Deposit environment is more or less synonymous with ore-forming environment and is used to classify deposit types that form under distinct physicochemical conditions from specific fluids or by particular processes in the crust. Deposit environments differ from system types because they are more generic. In addition, system types can operate in one or more environments. For example, an intrusion-related rare metal system may generate magmatic LCT pegmatites and magmatic hydrothermal Greisen and vein deposits containing tin. Although most of the deposit environment terms shown here are self-explanatory, to avoid confusion, they are defined in the report. For example, in erosional environments, gravity-driven turbulent flow of surface water or tidal and wind-driven wave action concentrate heavy, insoluble, or hard minerals by winnowing away light, soluble, or soft minerals. We found that most of the deposit type names in current use consist of a term that describes a key attribute that is preceded or followed by one or more commodities that are typically recovered from the ore. For example, orogenic gold, porphyry, copper, or iron, skarn. In some cases, the deposit group term is preceded by a modifier that describes another characteristic that enables further discrimination, such as epizonal. To standardize deposit type nomenclature, we adopted the following convention: optional modifier plus deposit group plus typical commodities. We made a few exceptions for deposit type names in common use that don't follow this convention. For example, heavy mineral sands is a deposit type in the placer group that is typically mined for titanium, zirconium, hafnium, rare earth elements, or abrasives. We found that some of the deposit type names in common use actually represent mineral systems rather than deposit types. For example, intrusion-related gold systems generate an assemblage of distinct deposit types that are commonly referred to as intrusion-related gold deposits. The same goes for the array of distinct deposit types that are commonly referred to as iron oxide copper gold deposits. In these cases, we split out deposit types with distinct characteristics and assign names. Other deposit types were considered to be subtypes, but this level of detail was deemed to be too fine for the geochemical database. For example, there are several subtypes of magmatic nickel-copper PGE deposits based on magma composition. In this case, the commonly used subtypes are listed in the synonyms column of Table 2. We also found that some deposit types occur in more than one system type. For example, intermediate sulfidation epithermal silver gold deposits occur in both subduction-related calc-alkaline porphyry-epithermal systems and rift-related high silica A-type porphyry-epithermal systems. We didn't give such deposit types different names because their system type affiliations, at this point genetically related features, can be used to distinguish them. The classified geochemical database has many uses. It will enable us to identify deposit types that have been poorly characterized so they can be sampled and analyzed. Document the critical mineral signatures of each deposit type, which may focus exploration. Identify individual deposits or systems that are highly enriched in critical minerals, which may prompt research to explain why. Compare critical mineral abundances in different deposit types, which may prompt evaluations of their mineralogies and the recoverability of critical minerals. Calculate the dollar value of critical minerals in ore, which may foster their recovery, and place and quantify critical minerals in a systems framework, which can aid resource assessments. Previous work on marine phosphate deposits shows how useful geochemical comparisons can be. You can see here that the shale normalized rare earth patterns for these deposits are remarkably different considering that they all precipitate from seawater. The left panel shows that the abundance of rare earths in 3 different phosphate deposits rival those in deep sea mud, China clay, Bocan mountain peralkaline pegmatite, and mountain pass carbonatite. The ease of dissolving rare earths from phosphate, together with this comparison, led Emsbo to suggest that recovery of rare earths from phosphate deposits could solve the rare earth element crisis. We can apply this approach to other critical mineral-bearing deposit types using the full suite of elements in the Global Geochemical Database. Geochemical data from well-characterized deposits can also be used to calculate critical mineral primary commodity ratios. In combination with information on the tons of primary commodity produced or in resources, it is possible to estimate the critical mineral endowment of processed mine waste and unmined resources. The estimated endowments for deposits can be used to generate critical mineral resource maps. Critical mineral grades can be calculated in a similar manner and used to generate grade tonnage models. This example shows the composition of cobalt copper ore in the Idaho Cobalt Belt. Critical mineral primary commodity ratios were combined with cobalt production to estimate the tons and dollar value of bismuth and processed mine waste. In such cases, recovery of critical minerals from mine waste could offset the cost of remediation. This example shows how critical mineral primary commodity ratios in concentrates were used to develop grade tonnage models for rhenium and porphyry deposits. By combining forces to fill the knowledge gap on the abundance of critical minerals in ores and classifying them as described, We now have a powerful means to address critical mineral resource problems today and in the future. Thank you.